Okay, so today we're going to be talking about quotient spaces. So roughly, these are um, spaces obtained by gluing. So we talked about this, well, I guess, somewhat briefly at the end of the last lecture, but we'll make some things precise today. So first of all, the notion of gluing is made precise by the idea of a partition. So a partition P on a set or a space X is a collection of subsets, disjoint subsets, disjoint subsets of X whose union is X. Okay, so it's a way to write as a set, or we'll only be thinking about spaces as a disjoint union of subsets. So this P, technically you could think about it as a subset of the power set of X. It's a collection of subsets. So let's see some examples. Okay, so this first example I'm going to call the circle for reasons which will become clear eventually. So we'll take X to be the interval 0, 1 with the following partition. So P is the partition with elements. So these are subsets of X. So there's one element subset for each X in the interval 0, 1. And then there's the subset containing 0 and 1. So the intuition is, well, if I have an interval and I want to get a circle, then, well, I can just glue 0 to 1 and get a circle like this. And so the partition is capturing the gluing. This 0, 1 here is indicating that we want to glue the point 0 to the point 1. Let's see another example. So this is the sphere, two-dimensional sphere. So let's take now X to be the closed disk, which I'm going to denote by this bold-faced D. So this is the one way to describe it is it's the closure of the ball of radius 1 inside of R2. These are all the points of distance at most 1 from the origin. And we'll consider the partition P with elements. So there's going to be a singleton for every point for X with norm less than 1. And then there's going to be one additional set consisting of all the points of norm 1. So X with the norm of X equal to 1. Okay, so the picture here is we start with a closed disk here. And well, any 2 points that are in the same element of the partition, we're gluing them together. So here, since we have all of these points in the same, these points on the boundary are all getting glued to the same point. And so what you're supposed to imagine is if you take the disk and then you identify all the points on the boundary to a single point, then what you get is exactly a sphere. So right now we're working at the level of intuition. In a second, we're going to put a topology on this set P, which will make all of this formal. Okay, let's do a couple of other examples. Yeah, so let me just give you a couple more examples quickly. So for the torus, you could consider, so we view the torus as you take the unit square and you glue opposite sides like this. So we take x to be 0, 1 times 0, 1. And the partition, so there's a singleton xy for every pair xy where they're both within the open interval 0, 1. And then, so the gluing instructions, so first we glue the left edge to the right edge, which is to say that the point 0y is identified with the point 1y for every y in 0, 1. And similarly, we glued the top to the bottom. So x0 is identified with x1, x in 0, 1. And so every point has to appear in one of these subsets. There's one point, or there's 4 more points that we haven't accounted for, which are the corners of this. And under these gluing instructions, all of these 4 corners are identified. So the point 0, 0 is the same as 1, 0 in the quotient, 0, 1, and 1, 1. Okay, so this is the partition which eventually will prove gives us the torus. Okay, and then there's one more example, which is actually quite important. So the setup here is, so this is a general kind of construction. We start with x and y spaces and a map f, which is surjective between them from x to y. And then we set P to be the partition whose subsets are the preimages of each point. So, okay, so these are the subsets. So for every y, we get the preimage, that's some subset. And these give a partition. Since the map is surjective, each of these subsets is non-empty, and they're disjoint, and their union is everything. Okay, so this is a partition. And we will see it come up quite soon. So the next thing, okay, so the next thing is, well, we want to put a topology on the set P. And this is what we're going to call the quotient topology. Okay, so the definition, well, okay, so maybe before I state the definition, let me just make one observation or remark. So given x and p as above, so p is a partition on x, there's a map we'll denote it pi from x to p, which sends, let me say it this way, so pi of x, the natural thing to do is to send x to the unique element of P containing x. Containing little x. So being a partition means there's one subset containing x, and there's exactly one. So just send x to little x to that subset. Okay, and so the quotient topology is going to be the topology that makes this, a topology that makes this map continuous. Okay, so we define, so this is the quotient topology on P. Yeah, so let me just write it. So the quotient topology on P works as follows. We say a subset U of P is open. So we need to say when sets are open, if pi inverse of P, or pi inverse of U in X is open. Okay, so we declare U to be open if its preimage under this map is open. So note that this is going to automatically make this map pi a continuous function. But before we get there, I guess the first thing to do is to check that this is a topology. So let's check that this defines a topology. So we need to show that the empty set and all of P are open. But that's true, just sort of trivially. I mean, the preimage of P is all of X and X is open. Okay. So unions. So suppose we have U alpha contained in P open, and we want to know if the union of the U alphas is open. Well, to determine whether it's open, we need to look at its preimage under pi. And the preimage is, well, we can rewrite this as the union of the preimage of the individual U alphas. So these are things that map into the union, and the things that map into the union map to a particular one, and so we have this equality. And then, well, this is a union of open sets. So in X, this is open. And so this means that by how we've defined things, that the union of the U alphas is open. Okay, so the axioms follow essentially because, well, they follow from in a straightforward way, from how we define things and because of facts about that X is a topological space. So intersections is similar. Finite intersections, this is similar. Okay, and then like I said, so remark, so by construction, the map P or pi from X to P is continuous. Moreover, the quotient topology, so this is, yeah, right, the quotient topology on P is the largest topology with this property. I mean, so if we wanted the map to be continuous, we could just give P the indiscrete topology. Then the map would be continuous. But that wouldn't be a particularly interesting topology and wouldn't give us the topological spaces we expect. So this is the largest topology with the most open sets that we could choose, and this turns out to be a good choice. Okay, so let's return to this example, the first example I gave of the circle. So with X, the interval is 0, 1, and P as above. So points in the interior are all in the same, all in a singleton, and then 0 and 1 are in their own subset. So the claim is that P with the quotient topology is topologically equivalent to the circle. So before we prove this, let me just observe. So note there are maps. Well, we have the following diagram. So we have X, which is 0, 1 here, which maps to P via this map pi. And then there's a map to the circle, which is like the exponential map. You know, xt is e to the 2 pi I t, or cosine 2 pi t, comma sine 2 pi t. Okay, and so to show that these are topologically equivalent, we want, well, we want a map like this, H, so we want, oh, well, yeah, well, we want to map H, which is a topological equivalence. And in fact, it's not so hard to see how to define H. So, well, we could define H to send the point. Okay, well, let's see. So we define H of, so a singleton as this point, e to the 2 pi I t, and then H of 0, 1 to be 1. I guess I'm switching back and forth between thinking of this as an element of the complex numbers and as an element of R squared. So, okay, so if we were working in R squared, this would be 1, 0. Okay, but right. So what one needs to check is that, so so we'll show H is a topological equivalence. So, well, it's not hard to see that this is a bijection, that there's an inverse, but we need to show H is continuous and that the inverse is continuous. And maybe at first sight, this might look a little bit tricky since we're working with this kind of strange topology, quotient topology on P. Okay, so next we're going to discuss this in a slightly more general setting, which will allow us to answer, excuse me, address a lot of these examples that we started with. Okay. So next, right. So before we go any further or say anything about the examples, we need a little bit more in terminology and tools. So quotient maps. Right, so let's start with a lemma, which is, well, so I mean, one question that we need to understand is when is a map to or from a quotient space continuous? So this is continuity for quotient spaces. So the setup here is we have X a space, P will always be a partition, and we have some function F from P to some other space Z. So then F is continuous if and only if pi compose F is continuous. So this is the statement. Let me draw a diagram to show you what's going on. So we have X, which maps to P by the map pi. We have some map F to Z, and then there's the composition here, F composed with pi. And the statement of the lemma is, if you want to check if F is continuous, you can phrase that in terms of continuity of a map defined on X, this composition. And so one is continuous if and only if the other is. Okay, so let's prove this. So proof. So one direction is easy. Can you see which direction is easy? So the forward direction, well, if F is continuous, pi is continuous by construction, so the composition is continuous. So this is composition of continuous. All right. Now the reverse direction is more interesting. So we're given that, so suppose F composed with pi is continuous, and we want to show that F is continuous. So to do that, fix an open set U and Z, and we want to show the preimage is open. And this is a subset of P. So F inverse of U is open in P if and only if, so by definition of the quotient topology, pi inverse, the preimage of F inverse of U in X is open. But the preimage of the preimage is just the preimage of the composition. And while this is open, so this holds because, well, F composed pi is continuous. Okay, so we wanted to show F inverse of U is open. That's equivalent to this condition, which holds because the F composed pi is continuous. So that's the lemma. Okay, so now we know how to test if a function from a quotient space is continuous. The next thing we need is the following definition, which is the notion of a quotient map. So X and Y spaces, we say Q from X to Y is a quotient map. If Q is surjective and continuous, and U, a subset of Y, is open whenever its preimage is open. In X. So another way to say this is that, so i.e., so this is different than continuity. So another way to say this is Q sends open sets of the form Q inverse of U to open sets, which is, yeah, I mean, because Q of Q inverse of U is U when Q is surjective. So this quotient map condition, it's saying something about how Q behaves on open sets. So a remark is that in general, a continuous map need not send open sets to open sets. So for example, consider the function from R to R, f of x is x squared. So here, minus 1, 1, this is open, but its image is the interval 0, 1, closed on one side, open on the other, which is not open. So the image, so I guess technically there should be double parentheses here. Right. Let me give you another example on a new page. So example. So the exponential map here, so t maps to e to the 2 pi I t. This is a quotient map. So let me illustrate this. Right. So the way this map, well, okay, so I just need to convince you that open, well, okay, so I mean, the picture is, so if I take an open subset here, let's see, maybe I don't want to say, let me first observe that this map is not a open map. So here's an open set that doesn't get sent to an open set. So this set is open in the subspace topology on the closed interval 0, 1. But the image of this subset is not open. But in the definition of a quotient map, we're not asking for the image of every open set to be open, only open sets that are of the form, the pre-image of some set. So here's an open set of that form. So the problem is this open set doesn't contain the full pre-image of this point. So the full pre-image of this set is the set I've pictured here, which is not open. On the other hand, if I were to add this point and make it an open set containing that point here, I would have something like this, and the image of this set is this full interval here, which is open. Okay, so this, if this is U, then Q inverse of U is this set, and it's open in this interval 0, 1, and indeed its image is open here. Okay, and this is sort of the only place where something interesting happens. So if you take any open interval in here, the image is going to be some open arc like this. Okay. So this is, I realize, potentially confusing, but I encourage you to just think about it if you're confused. Think about it some more, or ask me about it. Okay, so let me state another lemma, which is similar to the lemma we already had about continuity for quotient spaces. So this is, okay, so here, let's take x to y. This is a quotient map. So then, if we have a function y to z, this is continuous if and only if f composed with q is continuous. So we have x to y to z. This is similar to the diagram before. Q now is a quotient map. And we have f. So to test if f is continuous, it's equivalent to test if f composed q is continuous. And the proof is exactly the same as before. I'll leave that to you as an exercise. As before, meaning in the other lemma. This is completely analogous and follows directly from how we defined a quotient map. Okay. So this is an important thing. Oh, no. Well, this is important, but not, okay, this isn't the important thing I was about to say. Okay, so let's, right, so here's an important thing. Let me explain. Explain next. So let's, so let me state it as a theorem. So let's let x to y be a quotient map. And let P be the partition. Wow, okay, that's not what I meant to do. The associated partition of X, as I defined before. So you just look at the preimage of each point, and that gives you the elements of the partition. So then P, with its quotient topology, is topologically equivalent to Y. So before I prove this, let me tell you why this is a really useful theorem for us, and we're going to use it quite often to understand quotient spaces. So let me state this as a corollary, although I'm not going to, well, okay, so the corollary of this is that given X, I mean, what this is doing is this is helping you identify what the quotient space. So what this means is if we're given a space X with a partition P, and we want to know if P is topologically equivalent to some other space that we know, so to show that P is topologically equivalent to some other space Y that we know, it suffices to find a quotient map from X to Y whose associated partition as defined here is P. Okay, so if we do that, then the theorem tells us P is topologically equivalent to Y. Okay, so this is why this theorem is useful. Okay, so now let's prove it. Let me do this on a new slide. So let's define, right, so what we want to do in this theorem is prove that P and Y are topologically equivalent. So we need to define a topological equivalence. So we're going to define maps in both directions, H and G, which are going to be inverses. So G of little y, well, okay, let's think about this. We're given a point in little y, and we want an element of this partition. Okay, well, given little y, there's sort of an element staring at us in the face. So we'll define G of little y to be Q inverse of y. So we're viewing this as an element in P. And then in the other direction, if we're given an element of P, which all elements of P look like this, Q inverse of some y, we want to get an element of y. Okay, well, there's only one reasonable thing to do, which is just to send this to y. And okay, so we know these are inverses. If you do G and then H, you get back to where you started. So these are clearly inverses. And what remains then is to show H and G are continuous. So this is really where the heart of the matter is. Let me focus on H. Once you see the argument, G is going to be similar. So, well, okay, so we have this situation. We have the situation of the lemma. We have a function H from P to Y. And we know that H is continuous if and only if H composed pi is continuous. So by the lemma, H continuous if and only if H composed pi is continuous. So now let's think about what this function H composed pi is. So H composed pi of x. Well, okay, so what does pi do? So pi is the function that sends a point x and x to the element of the partition that contains x. What is the element of the partition containing x? This is our partition here. It's well, it's the pre-image of Q of x. Okay. And what does H do to the pre-image of some y? It sends it to that y. So this is Q of x. Okay, so now let's make sense of this. What have we done? We've just shown that H composed pi is Q. And so H composed pi is continuous. This is the same as, well, H composed pi is Q. So whether or not Q is continuous. But Q is continuous by assumption because Q is a quotient map. So this is part of the definition. Okay, so that's all that you have to do to show H is continuous. So this is by definition. By assumption or by definition. And showing G is continuous is the same sort of thing, but using the other lemma. So we stated two lemmas. One was for quotient spaces, one was for quotient maps. Use the other one for G. Okay, so that's the theorem. Okay, so I want to switch gears now for the remaining of the lecture, remaining part of the lecture. I think that's probably enough quotient spaces for now. So let's talk about something a little bit different. And we'll come back to applications of this theorem next time. So the next topic I want to talk about now is topological groups. So very briefly, a topological group is a space which also has a group structure so that these two things are compatible. So the definition, so I guess this is the first time we've talked about groups in the lecture. So let me define a group. It's not really a prerequisite for the course, technically. I think maybe people have seen groups mostly, but if you haven't, then, well, okay. So a group is a set with a multiplication. That's a function. A multiplication is a function like this, which takes input two elements of G and outputs something which we call the product, we denote like this. And this multiplication should have a few properties. So it should be associative. Which is to say ABC is ABC, depending on how you parenthesize it, or independent of how you parenthesize it. So it should be associative, it should have an identity, which is an element E, so that E times A is A times E, which is A. So multiplying by E on either side doesn't do anything. And there should be inverses, which is to say for every A, there exists some B, so that AB is BA is the identity. Okay, so common examples you should be thinking of are like the integers under addition, the real numbers under addition, or the non-zero real numbers under multiplication. You have to remove 0, since otherwise there's no inverses here when you multiply. Right, so here the identity element is 0 in these first two, and in this example the identity is 1. Okay, so now topological groups. Of course, so the thing we do in this course is take some object and put a topology on it, or consider objects that also have topologies. So a group with a topology is a topological group. A group G with a topology is a topological group if the multiplication and the inversion map G goes to G, this sends A to A inverse, are continuous. Okay. So some examples. So I want to finish just by giving you some examples. So we've seen some examples, but let me just go through some of these. So R with addition, well, this is a topological group. So, I mean, the addition operation, AB goes to A plus B, this is a continuous function from R times R to R. And the inverse is A goes to minus A, which is also continuous. And these are polynomials, which are continuous. Another example, Z with addition is also a topological group. Here, yeah, so in this example, I'm thinking of R with the discrete topology, and here Z, you can give the, oh no, sorry, I'm thinking of R with the standard topology, and here Z has the discrete topology, which is like the subspace topology of R. Well, so one thing you maybe know about groups is if you have a group and a normal subgroup, like these two, then you could take a quotient. So the quotient group R mod Z is also a topological group. Well, what's the topology? Well, with the quotient topology. So, well, there's a partition here. So, well, yeah, so R mod Z, what does this mean? Group theoretically, this is a set of cosets. It's Z plus A. These are cosets where A is in R. And this is a partition. Partition of R. And so, well, we can give this a quotient. We can give this the quotient topology. And let me just point out that, well, any coset Z plus A is represented by one of the form Z plus A, where A is in 0 and 1, the closed interval. And moreover, Z plus 0 is the same as Z plus 1. These are the same subsets. And so in this way, R mod Z, well, we could think about it as the closed interval modulo the relation that 0 is equal to 1. So, well, we haven't proved, well, okay, so this is basically saying this partition is the same as the one that we were looking at on the interval 0, 1 before. So we expect this topological group to be the circle. Okay. Let me give you a couple more examples and then we'll stop. Right, so let's take, so this one is in homework. Well, GL2R was in homework. So here, these are n by n matrices with real coefficients with determinant non-zero. These are invertible matrices. Invertible means that the multiplication has an inverse. So this is a group under multiplication of matrices, and it inherits a topology as a subspace of matrices. So this is like Euclidean space of dimension n squared. Maybe I want to put that somewhere else. Sorry. So this is a topological group. Let me put this off to the side. because I want to indicate some subgroups of it. So particular subgroup SLNR, these are matrices where now we ask for the determinant to be equal to 1. And since the determinant of the product is the product of the determinants, this is closed under the operation. So this is a subgroup. And inside of here, we have SON, which is, well, these are things with determinant 1, but which are also isometries, which you can express like this. A transpose A is the identity. Okay, so these are some topological groups, which are interesting. And then, okay, let me finish with just one more example, which is the group of all topological equivalences on a space X. So by definition, so I'm denoting this top X, so the objects here are functions X to X, which are topological equivalences. So I think this came up in discussion section for some people. So the operation here is composition of functions. So the multiplication is composition. And well, you can think about why composition of topological equivalence is a topological equivalence, and also why they're, what the inverse and the identity element are. And then, yeah, so then the topology, so this is a topological group, topological group with the so-called compact open topology. So this is the topology generated by sets of the form. So if you have K, so you have K in X compact and U in X open, then you can look at all of those topological equivalences which send K into U. And it turns out, well, these form a basis, technically a sub-basis, but I don't want to get into it, for a topology on this set of topological equivalences. Okay, so, well, okay, so it's maybe not clear why we're talking about topological groups now, but they will come up in our discussion of quotient spaces shortly. Okay, so I'll stop there for this lecture.